So in our previous video, we have discussed about a phenomena regarding that first order, second order, third order and more different order of structures like fault structures. So in general, it is as I have mentioned in the previous video, more in general compared to first order structures, second and third order structures are more important for any type of mineralization, hydrothermal related mineralization, magmatic mineralization, metamorphic fluid related mineralization. And with that background, now in this video we will be further substantiate the importance of splay of fault. Okay, so as you know what is splay, it is a part of fault only which refers to a network of smaller secondary faults that diverge from a main fault zone. So these plays develop due to the distribution of strain within a fault system. So these kinds of splay structures can be regarded as secondary structures because it is adjacent to the actual primary regional fabric, that lineament or faults. It is just associated with that. So whatever fluid is generated by that main fault, most of the fluid tend to flow along this splay fault, and those area, small area focused fluid will provide mineralization like sulfides, golds. Sulfide means different type of lead, zinc, silver sulfides, gold sulfides. Overall in general, sulfide mineralization are very common in different type of hydrothermal setup, fracture related setup. Fracture is a general term, of course. So we'll be discussing in detail about all these things. Sorry. So firstly, in introduction, we'll understand the quantification of natural fault geometries using mapped surface traces have been widely conducted. However, these analyses mostly dealt with lengths or separation distances of fault segments, not the net slip. Only roughness, fault surface, these things are very much important for characterization. Okay, quantification purpose. The length of the longest play produced by a fault is mostly correlated with fault length. Measure fault length and that splay length, maximum possible splay length. That ratio is very much important. So they are related by a power law, but not correlated with fault slip. So it is immaterial what is the net slip or fault strike along fault, that slip amount. In general, overall fault length, that is important. It mostly occurs in tip portion as well as middle part also possible sometimes, that splay formation with reference to major fault. Splays may form a dense and well connected damage zone around the main fault, and this damage zone is very much important, and this significantly play important role in concentration of localized fluid, which in turn provide mineralization. So here you see some caution should be maintained in field when you see some splay where these kinds of branching is occurring. Sometimes you may mislead by seeing intersection of two different generation of fault. Genetically, it must be related with the parent fault. Usually it is occurring along that tip portion at the end, or else even in between also, but this should be the like feather joints. So this should be genetically related to that single event of faulting. But however, sometimes there often you can see intersection of two different generation of faults, and sometimes it may be showing negligible slip or negligible offset, and that time you have to be cautious. Yeah? Or else sometime before introduction also, here one fault tip completes and here another tip. So maybe sometimes it can be misleading. So care should be taken in field. Now, so overall, splay is very much important nowadays in resource geology or any types of exploration related activity, these kinds of structures, as I have mentioned earlier, as we go deeper and deeper for any major structures, gold mineralization is enhanced, as I have mentioned previous video. Similarly, compared to the major fault, wide fault, these kinds of splay or secondary tertiary microcracks, those kinds of small features are very much important. So for splay analysis, splay study, important aspects are geometrical configuration, stress distribution. These are the aspects which must be understood. Then you can easily visualize the splay formation and its role in any types of mineral concentration. Seismic behavior, rupture propagation, geophysical imaging and structural analysis can help in understanding better about the splay. And finally, we will be analyzing the economic significance. Why splay study is important? Because these kinds of play, once you understand, once you learn properly in any kinds of deformed terrain, these kinds of play, you can narrow down your target. So the splay faults are often oriented at angles. Please, you can note, you can remember that is mostly that angle relative to the main fault, creating network of branching divergent fault segments. They usually forms at tips or along the length of the main fault particularly, of course, as I have slip of tongue, but in reality also it may form perpendicular or high angle as well as very low angle, but in general it occurs at relatively up to 30 to 60 degree angle is most common, particularly in areas where the main fault experiences a change in geometry such as bending, step overs, like right step over, left step over, any kinds of these kinds of changes wherever take place, and those areas plays are formed. These plays may form sometimes as complex horsetail like structures where individual splay fragments are diverging outwards in a fan like pattern. All the fragments are called splay. Here I have shown some photographs. You can see this itself is not a primary structure. Here this is one fault, this is one fault, suppose. Now this itself is a part of regional larger fault. So with reference to the regional structure, it is secondary. Regional structure is not visible. This itself is a part of fault zone. Now within this, these are suppose secondary. So these are splay tertiary. Now see further distribution. So vector is important. You must understand the stress distribution. Now there are two types of splay you can understand. As I have shown that this is horsetail splay. Okay, from main fault zone it is diverging. Okay, now sometimes from a fault, major fault, a small scale I have shown for understanding, one branching is taking place at low angle from the tip. So these are called the isolated fault configuration. Another part, sometimes this play can act as interacting phenomenon, the interacting fault configuration, because this is another one fault, this is another fault, and this play at high angle are acting as connecting link. Okay, and this is the frequency and kink angle. Kink angle is this angle, the actual fault and this play in between that acute angle. Okay, so mostly it is observed for interacting splay it is 50 to 60 degree, and for isolated splay mostly occur with configuration kink angle of up to 20 degree in general. Now one important thing for analysis purpose, you can understand splay, because once you will map, after demarcating all the splay, if you quantify properly, it will be a huge success. So what you will do, you measure the length as much as possible, all splay length, and as you know the actual parent fault length, so then you can plot all parent fault length versus major maximum splay length. Okay, so splay length splay when with reference to major fault splay different splay can have different length. You try to collect data from all maximum possible huge big splay length. So try to note down the highest longest splay fault, and those splay fault you must compare with reference to major fault. You'll be seeing there is a relationship. Easily you can understand. With histogram also you can see this frequency versus this ratio. Maximum length of splay versus primary fault. Thus length ratio, when it is 0.3, it is found maximum. Okay, so 0.3 means if splay length is 3 meter, fault length will be 10 meter. Okay, so likewise you can understand the splay relationship. In general, after histogram plot it is established, in general 0.3 is very much observed phenomena, and this is also this from this we can see this relationship between maximum splay length and parent fault length. The best fit to the data is shown with this blue color. Okay, and here if you see B, frequency versus ratio of maximum splay length and parent fault length, which is I have shown mode is 0.3. And whereas as I have mentioned at the beginning, fault length is important, not any kind of slip. Now if we see maximum splay length versus parent fault slip, not fault length, fault slip length, that slip it is not at all correlatable. Okay, now so different parameter as I have discussed, those parameters will be briefly discussing, like geometric configuration. So splay faults are often oriented at angles relative to the main fault, and thus it creates network of branching diverging faults, and which is very important because these kinds of fault network act as very important loci for hydrothermal fluid movement. Here and there so many surface area is getting created, and along that fluid when migrate it will be keep on reacting with the wall, and so many stock works, micro cracks, veinlets, stringent quartz veins, those things often act as very important criteria for getting sulfides mineralization, lead, zinc, silver, gold. So they usually form at the tip or along the length of, as I have mentioned, length of the fault, perpendicular, particularly in area, fan-like pattern. These things already I have mentioned. Now come to the important part, that is stress distribution. See, fault splays form in response to a change in stress. As I have told, any fire bending, step overs, these kinds of change where take place, that time what happened? Some stress regime gets changed, and that change is reflected in the form of splay. Okay, when the stress is concentrated at certain points along a fault, particularly near bend, step overs, other irregularities in the fault trace, the strain can be relieved by the development of splay faults. Okay, so those are the zones, where compression or decompression, maximum compression or minimum, that means extension, these kinds of area pocket can be developed, and those pockets, what will happen? Either sagging or as I have mentioned, pop-up blocks. Those are nothing but related to splay formation. For a broad understanding, you must see these things. All are ultimately mechanics, dynamics must be understood. What is in a name? Nomenclature may be vary. In a compressive regime, splay faults may form thrust faults, while in an extensional regime, they tend to form normal faults, definitely. And strike slip fault systems, splays are often radial shears or antithetic faults that help. Radial are mostly synthetic, and antithetic means R dash. They help accommodate lateral displacement across fault zone. Now, one small thing but very significant, that is seismic behavior and rupture propagation. because false plays play a significant role in the propagation of seismic ruptures. They can act as barrier or channels for rupture propagation during earthquake. When stress develop, so what will happen? That rock will get rupturing, and that rupture will be propagated throughout the rock, as I have shown. So network of small fracturing will be developed, which are actually in general we termed as fracture. Those are actually small splays. Okay, so during large seismic events, these secondary faults can be activated potential, increase the area of rupture and consequently the magnitude of earthquake. In some cases, play faults can occur localized uplift, subsidence, as I have mentioned, pop-up blocking, affecting the landscape and surface rupture patterns. So modern techniques such as seismic reflection profiling, ground penetrating radar, GPR, and 3D seismic imaging has significantly enhanced the ability to map and understand the splay fault structures. So mostly seismic is very important, you should understand, and sometimes magnetic as well. From magnetic also you can understand splay, and of course wherever proper outcrops lithostructural mapping you can directly demarcate. So this for hidden concealed type of things, soil cover area, this seismic for huge coverage, if covered sediments thickness is more, and or else even magnetic also you can understand, even resistivity, all types of geophysics you can, if you properly understand the phenomena, you will be able to demarcate. But magnetic, by using magnetic also it is possible. High resolution seismic data can show vertical data, lateral extension splay. This is for major structures. Splay can be of secondary, tertiary splay. It depends on the scale. Now, main important thing come to the economic potential aspects. See, hydrothermal fluid conduits splay act as better hydrothermal fluid conduits, as I have mentioned earlier video as well, because plays act as either secondary, tertiary, never it can be primary. That means it never can be a first order structures. It is either second order, third order, and so on. So these types of second, third order and more, those are more important structural position for getting economic mineralization because of hydrothermal fluid circulation activity, because they are better conduits, immediate reaction, chemical reaction take place, then with movement, moving of solution toward from major structures towards inside, its temperature pressure condition get reduced, and as rupture strength increase, what happen, rupturing take place means sudden release of stress, and that indicates drop of pressure, that also causes mineralization. Okay, and these are found from typically in brittle ductile regime also. And in brittle phenomena, brittle regime also this happen. Now for trapping structures for ore bodies, play act as very important feature in the field, because strain accommodation and fracturing is most important phenomena in case of splay, and therefore it is associated with ore hosting lithology. Sometimes some typical host rock, for example host rock, that means litho control surface, there also splay can cut those rocks, so automatically along splay secondarily deposition can also take place. So therefore it has a potentiality to become a exploration target. By using different geophysical phenomena, geophysical techniques, we can identify different splay. Even by lithostructural mapping, wherever outcrop available, as I have mentioned, once we identify splay, those must be targeted in further detail during detailed exploration stages. So for example, in many epithermal gold and silver deposits like Nevada's Carlin trend, false play help in channelizing of mineralizing fluids to favorable diffusional sites. Okay. Now in copper porphyry system, see all surface. So in Chile also, splay faults create favorable structural condition for ore body localization. Gold deposits in shear zones such as those in the Archean greenstone belts of Canada, Australia often form where fault splays have fractured the host rock, providing sites for mineral emplacement. Again, in the Mount Isa region, Australia, fault splays associated with the main faults provide structural guides for copper lead zinc exploration. So from this you can understand the importance of splay. Okay, so this splay deserve its more detailed study. So therefore we must understand geophysical imaging, structural analysis are very much significant. So if we update modern techniques such as seismic reflection profile, GPR, 3D seismic imaging, they have significantly enhanced the ability to map, understand splay fault structures. And these methods reveal intricate network of splays in fault zones. Case studies are also available, especially in areas like accretionally prism, like Nankai Trough and transform fault system in San Andreas. High resolution seismic data, on the other hand, can also show vertical and lateral extent of splay faults, helping researchers determine how they interact with the main fault and contribute overall fault mechanism. Okay, as I am repeating the modern phenomena. So if you have any question, you can further comment. So this is the end of this video. Thank you.